This is June 2009, paper Physics 4, question 5, and fairly standard start to electric field question, asking for us to define the field strength. And remember, field strength E is equal to F over Q, therefore we define field strength as the force per unit charge. So the field strength is the force per unit charge acting on an object. And we've got 2 marks here available for that. So it's the force acting per unit charge which acts on a positive charge, and we need that to get the second mark. So it's force per unit charge which acts on a positive charge placed in an electric field. Okay, so those are the 2 points. We need a positive charge part and force per unit charge. Right, calculation is the next part of this question. Figure 5.1 shows 2 point charges Q1 and Q2 of magnitude plus 2 microcoulombs here and plus 4.5 microcoulombs here, placed 20 centimeters apart, and we are told that at point A the resultant electric field strength at A, which is a distance x from Q1 due to the charges Q1 and Q2, is 0. So the electric field strength at this point A is 0. So that means that at this point here, okay, if we placed a positive charge here, it's been pushed by Q2 in this direction, it's been pushed by Q1 in this direction, so that if we look at the E due to Q1 and we look at E due to Q2, those two must cancel each other out. So that's what I'm going to say. Okay, at point A we're saying that the field strength, okay, due to Q1 is equal to, well, we've already said field strength is force per unit charge, so that's equal to K times Q over R squared. Which is equal to 9 times 10 to the power of 9, 8.99 times 10 to the power of 9 times, in this case it's plus 2, so it's 2 times 10 to the minus 6 microcoulombs, and then that's over x all squared, x squared. The field strength due to Q2 is equal to the same, K times Q over R squared, which in this case then again is 9 times 10 to the power of 9 times, in this case 4.5 times 10 to the minus 6, and then the distance is going to be 20 centimeters minus x, so that's 20 minus x all squared. What we're going to do now is we're going to equate those two. Okay, so we have 9 times 10 to the power of 9 times 2 times 10 to the minus 6 over x squared equals 9 times 10 to the power of 9 times 4.5 times 10 to the minus 6 all over 20 minus x all squared. If we look at that, we have 9 times 10 to the 9 cancels. Let's leave that as 20 minus x all there, and then 10 to the minus 6, 10 to the minus 6 is going to cancel. So if I multiply across by that, what I'm going to get is 20 minus x squared times 2 is equal to 4.5 times x squared. Take the square root of both sides. Okay, or before I do that, it's probably better to do this as 20 minus x all squared is equal to 4.5 divided by 2 is 2.25 x squared. Now we can take a square root of that. I'm going to have to just go over to the first side of this page so I can do this calculation. Okay, so I now have 20 minus x all squared is equal to 2.25 x squared. So if I take the square root of both sides, I'm going to get 20 minus x equal to the square root of 2.25 x. Bring the x across, so I have 20 is equal to x plus the square root of 2.25 x. Add those together, that would be equal to x upon 1 plus the square root of 2.25. So divide across by that, so x is going to be equal to 20 over 1 plus the square root of 2.25, which is equal to, put that into your calculator and calculate, and that turns out to be 8 centimeters. So x is equal to 8 centimeters. Okay, I suppose that the key to this question here is knowing that the field strength at A due to Q1 is equal to the field strength at A due to Q2, and then we're saying it's 20 minus x as the distance there. I just kept that in centimeters. I could have changed that all and put it through, but it would be times 10 to minus 2 all squared, so it's all going to be the same anyway when you work that out. Then a charge of plus 3 microcoulombs is now placed that state the value of the electric force exerted on the plus 3 microcoulomb charge. And they're asking you here to state, so really you shouldn't have to think too much about that, and that's because the force here is going to be 0 newtons. Why? Well, because the electric field strength is equal to the force per unit charge, therefore the force is equal to the field strength times the charge, and it doesn't matter what charge you place there, the field strength is always 0, therefore the force is always 0. So as E is 0 at A, the force must be 0. And that's because F is equal to E times Q. So if E is 0, then multiply it by Q and you're going to get F to be 0. We now are given a situation where the plus 3 microcoulombs charge at this point here, so we've got plus 3 microcoulombs at A and it's moved towards point B. We're asked to explain qualitatively why energy would be needed to move the plus 3 microcoulombs. Alright, so what's happening here is we're pushing this 3 microcoulombs towards that plus 4 microcoulombs. That's plus and that's plus, therefore you're moving it against the repulsive force due to Q2. Okay, so the plus 3 microcoulomb charge is moving against the repulsive force of Q2. Now, it is getting some help from the plus 2, okay, from the plus 2 microcoulombs here, but whenever we look, so the plus 3 micro is moving against that repulsive force of Q2. The repulsive force from Q2 is greater than the pushing force, which is helping you, from Q1. So work needs to be done to help the force from Q1 move the plus 3. We're going to move that plus 3 microcoulombs towards Q2. Okay, why energy would be needed? Well, because the work done equals the force times the distance moved. So we need to do this amount of energy, we need to do this amount of work, therefore you're required to put in that amount of energy in order to do that.